Okay, one question that I just keep getting over and over and over is angles. They're like, what do you do with angles? What are these things? And we're gonna start basics because this is stuff that, as I've mentioned several of my responses to several students, it's the same stuff we've been doing since first semester. Okay, it's the same stuff we did when we did force diagrams, we did projectiles. It's all just looking at the basic trig, and the reason for its use is because we want to understand and reinforce the idea of independence of planes. So we're not just crunching numbers, we know what to do with numbers. So for example, all right, if we have an object, I guess I didn't play up this as much as I thought I did. Pen, 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 thank you. All right, so if we have an object and it is right here, and we're being pulled at an angle, all right, some force at some angle. Remember, in physics, we usually want to say, well, if I'm going to do math with this, I need to break it up into its x and y components, right? I got to do it so it's x information is one set of stuff, y information is another set of stuff. So what that means is I'm going to take this vector, so it could be velocity, okay? So when we do momentum, you could technically have a velocity and angle, but you'd look at each plane independently. So it could be a force, could be velocity, could be an acceleration, although we haven't done that, but it could be any vector. So for this example, I'm just using forces specifically, but you could replace this F with a V as well. And so if we have a certain angle here, well, we're going to want to break that up into its x and y components. So this is the x component. All right, that's the x piece. And then we need a y piece. We'll go with light blue. All right, so f, y. Okay, so we've got x, we've got y. We want to break this into its individual x and y components. And to do this, we use trig. So let's go to red. So if we want to do this, x right here is cosine. All right, so because cosine is defined as adjacent over hypotenuse. Okay, so adjacent is, so here's my angle, the adjacent one to it, that's f of x, could be a v of x, but it's whatever the x component is, divide the hypotenuse, and the hypotenuse is that initial vector itself. So if I just do my simple math, this is how I always write it and present it to you guys, it is then f cosine of theta is equal to f of x. And remember, for this to work, we use degrees. Okay, so you're given an angle of 20 degrees, make sure your calculator's in degree mode. If you're given an angle of 20 degrees and then you use it in radians, it's the exact same thing as someone saying, well, that cost me $50, and you give them 50 cents. You're like, well, isn't it the same thing? No, totally different units, has totally different meanings, totally different values. All right, so make sure those units always agree. Now for the y component, y is the angle, or is opposite of the angle, so that goes with sine. All right, so sine is opposite, which in this case is f of y, over the hypotenuse, which is again the initial vector itself. So if you just rearrange that, you get f sine of theta equals f of y. All right, so that's what you need to work with. Okay, if you're ever given anything at an angle, you break it up into its components because usually we only care about the x-plane or we only care about the y-plane. Now, how does all this relate to the most common thing I'm getting? Kids are like, how does that relate to power? All right, well, let's go through how that relates to power. So to do that, I'm going to bust out an old problem that we did a while ago. This one right here, all right? So this is from, oh man, my brain just, worksheet 4 in energy unit. I simplified it a little bit here because the original problem had friction in it. I just don't want to play with that right now. So I'm just going to focus purely on the angled elements here. All right. So we want to draw a quantitative force diagram. of this situation. So this is my system. All right, we're going to look at the lemon, and we just want to draw a force diagram of that lemon. And let's go with red. No, well, I like purple. Let's go school colors. So, force diagram. Well, I take my system, which is the lemon, so that's 1,200 kilograms. And then I need to draw the appropriate forces on it, so we know we have gravity pulling it down. We have the ground pushing it up, but then we have this rope here is pulling at an angle. So I want to break that into the y component, and I want to break that into the x component. And so I'm going to write those down here. So this is f of x, and this is f of y. Now it's staying on the ground, so this is balanced with that. And like I said, the original problem had friction in it, but I'm just going to ignore friction in this situation, just to, again, simplify and focus on what the big questions are about. So we want to put some numbers on this. Okay, so I'm just focusing on the key ideas here. So if we want a number for f of y, well, remember, f of y, as we mentioned earlier, is equal to the initial force times sine of the angle. So we know he's pulling with a force of 20,000 or 220,000. There's my brain. So we've got 20,000 times sine of 30. And you crunch those numbers and you get something, which I forgot to write down. So I don't know. I don't have my calculator with me. Oh well. That's not the important one. So here we go. We got that is equal to 20,000 sine 30. You guys can crunch the math. But we also want the x component. This is the one I really care about. You'll see why in a second. Cosine of 30. So 20,000 cosine 30. Crunch those numbers. I do have this answer because, like I said, that's the one that was important. And so for that, you get 17,000. 300 and something. 17,000. 320-ish, something like that. Let's erase that because that's just atrocious. No one can read that. All right, so we've got 17,000 and 320.5 newtons. All right, so that's what we know goes here. 20,000 cosine 30. All right, so we know these values by doing some trig. Now, why do we care about these independent things? Well, when you are asking yourself what's happening in the problem, so it says how much energy was transferred, okay? If you are transferring energy, okay, it says energy transferred. The transfer of energy, and I'm going to scroll down a bit because I want some space here, because I just need my force diagram now. The transfer of energy, this is work, okay? And work is equal to force times distance. But remember, these two things must be in the same plane, all right? So if you're moving in the x-plane, must be in the same plane. All right, so if you're moving in the x-plane, then the only forces that you're going to be working with that will do work are in the x-plane. So this y component here is totally wasted because you're not traveling a distance in the y-plane, so you only care about the force. So since the distance is in the x-plane, we care about the force in the x-plane. If it was something that was moved vertical, like something climbed a hill, we don't care about the x-plane anymore because the x-plane's not giving us a change in energy, okay? So you really have to ask yourself, how is work being done? What is the value of change in energy? So you might need to use an LO diagram to solve that, things like that. But this is the point I want to get through with the angles because that's what everyone keeps focusing on. Hey, what's up with the angles? So You got work equals force times distance. They must be in the same plane. It says that the distance was 10 meters. So therefore, I say, well, the force in the x-plane is equal to 20,000 cosine of 30. And the distance is 10 meters. So you crunch those numbers, and then you get 173,205 joules of energy. All right, that's your work done. All right, that's how much energy was used up, because work is equal to change in energy. Okay? Now, the next question isn't exactly what's going to help us here, but like I said, students want to know, well, what do you do about power, Mr. Szymanski? I still need some guidance on this. And so when you go to power, remember, power is equal to work per unit time, and work is equal to a change in energy per unit time. So, again, this is a lot like that impulse momentum stuff where you've got some choices. What are you going to approach this from? Do you know the change in energy? Do you know the work? Do you know, hey, it went from 0 to a certain speed? Well, then you know it's change in kinetic energy. If it went from something to a certain height, you know it's change in gravitational potential energy. So you may need to approach from that side. In this case, we were given forces and distance, so I can approach it directly from the work side. And so all I got to do is then say, well, if that's the work that was done, then I just need to know the time. So let's just say, hey, this took 15 seconds. All right, so let's just say it took 15 seconds. Again, not in the problem, but I'm just making this up as I go. Then I could say, well, then the power is equal to 173,205 divided by the 15 seconds. And so if you crunch those numbers, you will get 11,547, and the units would be watts. All right, so that would be the power. So this is why power is pretty straightforward in the terms of its math. All right, you're either finding the work done or you're finding the change in energy, and you're just dividing by time. The trick comes into understanding, well, where am I getting my energy from? Because you might get your energy from, say, an LOL diagram or various other things like that. So this, LOL diagrams. Whereas work, that might come from force times distance, where again, force and distance must be in the same plane. So what angle you approach it for depends on the information you're given. All right, and so again, hopefully I've kind of showed how angles play a role in this. It's reinforcing the same plane idea. And when you use this energy and the power ideas, you got to kind of pick which of these is going to work for you based on the information given. All right, hope that was helpful. Thanks for the questions. Keep them coming. I love answering them. And yeah, you guys have a great winter break, I guess. Yeah.